A very good morning to Dr. Rosamis. So we are from Group 13, and my name is Ong Chen Shen, normal matrix BS221605111. And also my group member who is Nurul Huda Hazimah bin Hazman and Abdul bin Ali. So in this assignment, we have to conduct several methods in solving the linear components and non-linear components. So each of us will using a different method in solving linear system and non-linear method. So this is the tables who showing handling in the different method in linear system and non-linear method. So for Nurul Huda Hazima, we'll handling for the Gaussian elimination and bisections, and me will handle the Gauss-Schadder method and Newton-Raphson, and last but not least, Abdi will handle for the LU decomposition and secant method.
Assalamualaikum to Dr. Razami. My name is Nurul Hurazima binti Azman with metric number BS221100201, and I will present the Gaussian elimination method and bisection method. On this slide, I will explain the Gaussian elimination method used to solve a system of linear equations. First, the system is rewrite into matrix form where the coefficients form matrix A, the unknowns form vector Y, and the constant form vector B. Next, the augmented matrix were formed and written as AB, which combine the coefficient matrix and the constant vector into a single matrix. The Gaussian elimination algorithm consists of four main steps. The first one is forming the augmented matrix. The second one is forward elimination, where we apply elementary row operation to transform the matrix into an upper triangular form. These operations include swapping rows if necessary, multiplying a row by a non-zero constant, and adding or subtracting rows. Next step is back substitution, where we start from the last equation and substitute upward to find the remaining unknowns. Last step is we obtain the exact solution for y1, y2, and y3. Next, to eliminate the variable y1 from the second and third rows, we have to apply row operations. First, we subtract 0.5 of row 1 from row 2, and then subtract 0.75 times row 1 from row 3. After performing these operations, the matrix now has zeros below the first pivot element. To eliminate the second variable in row 3, we then add approximately 0.1406 times row 2 to row 3. As a result, the augmented matrix is transformed into an upper triangular matrix, which completes the forward elimination process. Once the matrix is in upper triangular form, we proceed with back substitution. Starting from the last row, we solve for y3, and from the equation, we obtain y3 equal to 8.014. Next, we substitute the value of y3 into the second equation to solve for y2. This gives the value of y2 equal to 6.913. Finally, we substitute both y2 and y3 value into the first equations to solve for y1. The result is y1 equal to negative 0.6. Therefore, the final solution of the system is stated as on the slide. Next, for this part, I will explain how the bisection method used to solve a nonlinear equation. This method is a bracketing method, which meaning it requires two initial cases where the function changes sign. This sign change guarantees that at least one root exists within the interval. The algorithm works as following. First, we choose two initial cases, a lower bound and an upper bound. Next, we compute the midpoint of the interval. Then we check the sign of the function at the midpoint. Based on the sign, we update the interval by keeping the subinterval that contains the root. This process is repeated until the error is sufficiently small or the stopping criterion is satisfied. Let's assume x lower equal to 0 and x upper equal to 1. When we evaluate the function, we get g0 equal to 1, which is positive, and g1 equal to negative 0.6321, which is negative. Since g0 multiplied by g1 less than 0, we confirm that a root exists in the interval 0, 1, and the bisection method can be applied. Next, the iterations are carried out by the following steps. The calculated midpoint of the interval 0, 1 is 0.5. After the function is evaluated at this midpoint, we then obtain a positive value. Since g 0.5 and g1 as opposite in sign, the new interval becomes 0.5 and 1. In iteration 2, the new calculated midpoint is 0.75. At this point, the function value is negative, so the sign change now occurs between g0.5 and g0.75. The interval is updated to 0.5 and 0.75. In iteration 3, the calculated midpoint is 0.625. Since the sign change still occurs between the lower bound and the midpoint, the interval is further reduced to 0.5 and 0.625. This process continues, and with each iteration, the interval becomes smaller, which brings it more closer to the actual root. These are the iteration table that includes several iterations. From the iteration table, we can see how the lower bound, upper bound, and midpoint values gradually converge toward a single value. The function value also approaches 0 as the number of iterations increases. After several iterations, the approximate root is found to be 0.567. Next, the convergent graph visually shows this behavior. The curves represent the function gx, and the point where it intersects the x-axis corresponds to the root. This confirms that the bisection method successfully converged to a solution and provides a reliable numerical approximation for nonlinear equations. Next, move on to the theoretical justification. Gaussian elimination is a direct numerical method used to solve system of linear equations. Its main strength is that it guarantees an exact solution in a finite number of steps, provided that the system has a unique solution. Unlike iterative methods, Gaussian elimination does not require any initial guesses, which make it straightforward and reliable for solving linear systems. Because of this deterministic nature, it is commonly thought as a foundational method in numerical analysis and linear algebra. While in the bisection method is a numerical technique used to solve nonlinear equations. It is applicable to continuous functions where a sign change exists over a given interval. One of its key advantages is that it guarantees convergence as long as the function changes sign within the interval. Additionally, the method does not require derivative information, making it simple and easy to implement, especially for problems where derivatives are difficult to compute. However, despite its accuracy, Gaussian elimination has some limitations. The computational cost increases rapidly as the size of the system grows, especially for large matrices. While it is efficient and practical for small to medium-sized systems, it becomes less suitable for very large systems due to high memory usage and computation time. As a result, alternative methods are often preferred for large-scale problems. Despite its reliability, the bisection method has some drawbacks. Its convergence rate is relatively slow compared to other root-finding methods. To achieve high accuracy, many iterations are required, which increases computation time. Therefore, while the method is very stable and dependable, it may not be the most efficient choice when faster conversion is needed. Thank you.
So next we're moving on to the questions 2, which is using the Gauss shadow method to solve the linear system component for the equations. So my name is Ong Chun Xuan, and number matrix is BS2216051. So I'm handler for the Gauss shadow method to solving the linear system component, and Newton-Raphson method to solving the non-linear system component. So in my cases, I need to using the Gauss shadow methods compared to the Gauss elimination. So why we using the Gauss shadow method is because of Gaussian eliminations will getting a large round of the errors if the equation is in a larger sets of the values and variables. So in such a way, we need to use an interactive method such as a Gauss shadow method to giving the users in a low row of the error, which is reduce the errors. So for the algorithms in this Gauss shadow method, for the first step, we need to rearrange the equations for the three equations into a y independent. So next we will setting for the initial guess for the y0. So in our case, I will setting all the y1, y2, y3 into a zeros. So we need to using these formulas interact using the Gauss-Seidel method formulations to getting the values of the y1, y2, y3 in the interactive way. So step 4, we need to check the convergence. If the value is converged, so we will stop the algorithm. Okay, so this is the step-by-step we're using the Gauss-Seidel method to solving the linear equations covenant. So first step, we need to check the coefficient metric is that diagonally dominant. So in our step, we check already. So in these three equation is a true value which is diagonally dominant. So we will get it onto the Gauss-Seidel method algorithm. So after we rearrange of the equations and getting the y1, y2, y3s in the iterative form, we will initially to get the values in the iteration 1 and 2. So this iterative will continually doing the iterative way until the value is converged. So we need to check in the iterative table while the value is converged. So after we using the interactive Gauss-Seidel method in the previous step, so we are using the Pythons to getting more easier and efficiency way to create the iteration table and calculating for the Gauss-Seidel method. So surprisingly, I will getting the value stop at the iteration at 18, which is the y1 is equal to negative 0.5999 and y2 is equal to 6.9130 and y3 is equal to 8.1043. So you can see that in our graph, this is showing the convergence of the variables in the certain values, and also the error converges in 0 to 18. So this is the way we converge the Gauss-Seidel method. So this is a final solutions for Gauss-Seidel method in these equations. So we're moving on to the nonlinear components by using the Newton-Raphson method. So why is the bisection method is not good at all? It's because the bisection method are causing the false position method of finding the roots in a nonlinear equations. So by improving the problems, we propose for the Newton-Raphson method in these cases. So for the algorithm in Newton-Raphson method, for step 1, we need to define the function and its derivative. So in our case, my gx is equal to exponent power negative x minus x. So after we derive for the original function, we're getting negative exponent power negative x negative 1. So step 2, we need to choose the initial guess for the x. In our case, I will choose that in the 0.5. So in step 3, we need to iterate using the Newton-Raphson formulas by getting the number of the convergence. So last but not least, step 4, we need to check the convergence. If the converge is tolerance, so we will stop. Otherwise, we will repeat in the step 3. So this is for the Newton-Raphson method algorithm. So after we know how to the algorithm according to the Newton-Raphson method, we need to solving to our nonlinear equations method. So after applying the Newton-Raphson method, for the initial guess x0 is equal to 0.5, we do the iterations 1, iterations 2, and finally in iteration 3, we getting the convergent values, which is x3 is equal to 0.5671. So surprisingly, the guessing is very good. So we get the x3 terminate in the iteration 3 with a value of 0.567. So this is some of the graph represents by the Newton-Raphson method, which is graphical interpretations, root convergence, function error, and step size. So to have a better understanding about what's the algorithm Newton-Raphson method in a graphical way. So last but not least, we will have a discussions about the Gauss-Seidel method and also Newton-Raphson method. So in finalize, Gauss-Seidel method is great because it's simple and does not need much of a memory in the calculations. But it have a big weakness, which is we need to check the matrix is diagonally dominant or not, because this will guarantee the convergence value. So for the Newton-Raphson method case, in our case is very, very fast, which we have 3 iterations, but also have a problem that if the initial guess is bad, in our case, like I'm choosing the x0 is 2 instead of 0.5,
This will may have a fall completely for this using a Newton-Raphson method. So they have a further improvement way to conduct that will be presented by next person. So for a real world use, I will recommend to checking the diagonal dominance before using the Gauss-Seidel method in our case. And also for the Newton-Raphson method, I think we can combine with the several method like bisection method to justify the neighborhood values before we letting the Newton-Raphson method to do the fast convergence. So this is all for the Gauss-Seidel method and Newton-Raphson method analysis and discussions. So that's all from me. Thank you.
Okay, now I will explain how we solve the linear part of the problem using the LU decomposition method. We are given this system of three linear equations, and then first we rewrite the system in matrix form, which is AY equal to B, where A is the coefficient matrix, Y is the vector unknowns, and B is the constant vector. To make solving easier, we decompose matrix A into two special matrices, which is A equal to L times U, where L is a lower triangular matrix and U is an upper triangular matrix. This decomposition allows us to solve the system step by step instead of solving all equations at once.
Next, we construct the upper triangular matrix U using row elimination, similar to Gaussian elimination. We start with matrix A and eliminate the values below the main diagonal. Firstly, we use row 1 as the pivot and eliminate the first column values in row 2 and row 3. After elimination, we get an intermediate matrix. Then we move to row 2 as the pivot and eliminate the value below it in row 3. At the end of this process, we obtain the upper triangular matrix U, which has zeros below the main diagonal. This matrix is important because it makes solving later much easier using back substitution. Now in this slide, we are forming the lower triangular matrix. Matrix L stores the multipliers that we use during the row elimination process. From the first column, L21 equal to A21 or A11 equal to 2 divided by 4, and then we get 0.5. Then L31 we get 0.75. From the second column, we compute the updated pivot value, then calculate L32, which is equal to approximately negative 0.14706. So the final L matrix becomes L 100, 0.5, 10, 0.75, negative 0.14706, and 1. Now we have successfully decomposed A into L and U. Use lower and upper triangular matrix. Next step is solve Ly equal to B, is forward substitution. After decomposition, we solve the system into stages. First, we solve Ly equal to B because L is lower triangular, so we use forward substitution. From the first equation, y1 is equal to 15. Second equation, 0.5y1 plus y2 equal to 46. Substitute y1 equals to 5 into the y2, and then you got 38.5. Enter the equation, 0.75 y1 equal to minus 0.14706 y2 and plus y3 equal to 33. Then substitute values y3, and then we got y3 is approximately equal to 27.41176. The next step, we solve ux equal to y. Since u is upper triangular, we use back substitution. from the third equation, 3.38235x3 is equal to 27.41176. So x3 approximately is equal to 8.104. Second equation, 8.5x2 minus 2.5x3 equal to 38.5. Then substitute x3, and then we got x2 is equal to approximately equal to 6.913. First equation, for x1 minus x2 and plus 363 equal to 15, and then we substitute the values of x1, the value of x2 and x3, and then we got the x1 is approximately equal to negative 0.59975. So for the final solution of the linear system is approximately x1 is negative 0.6, x2 is 6.9, and x3 is 8.1. Now we move to the nonlinear part of the problem. We want to solve the equation gx equal to e negative x minus x equal to 0. Since this equation cannot be solved easily using algebra, so we use a numerical method called the secant method. This secant method used two initial guess, does not require derivatives, and approximates the root by drawing a secant line between 2 points. The formula for the secant method is xn plus 1 equal to xn minus gxn times xn minus 1 divided by gxn minus gxn minus 1. So we start with two initial guess, which is 0 and 1, and then we evaluate. We got the gx, we get the g0 is equal to 1, and then g1 is equal to negative 0.63212. Since the signs are different, the root lies between them. So next we perform the iterations. First iteration, we compute x2 0.6170, and then we got the gx2 is equal to negative 0.07081. For the second iteration, we compute x3 equal to 0.56384, then we got the gx3 is equal to 0.00518. And then the last iteration is x4, we compute x4 is equal to 0.56717, and then we got the gx4 is 0.00004. Since the function value is very close to 0, so we stop at the iteration 3. So the root is approximately x is equal to 0.56717. Next, in this slide, we explain the graph of the secant method visually. This graph shows how the secant method works visually. So for the blue curve represents the function gx, and then the red points show our successive approximations, and each new point is found by drawing a secant line between two previous points and finding where it crosses the x-axis. You can see that the method converges quickly, and then only a few iterations are needed. No derivative is required, unlike Newton-Raphson. So this demonstrates that the secant method is efficient for solving the nonlinear equations.
So this is end of our presentation, and thank you.